Okay, so as some of you may have picked up on before, this week is all about creating the test and debug boards for the tinyVU board that we have in development. And with that in mind, just to bring you guys up to date on what the tinyVU is, just in case you may be a first-time watcher of this, here's a brief overview of what the tinyVU board is. A VU meter board is actually used to monitor visually the inputs of your audio stream. So let's say you have a microphone preamplifier and you want to see if you have any content, or if you're driving the content too hard for the sound card that you have coming after it, you may want to use a VU meter to give you an idea of what's flowing back and forth. And traditionally, VU meters were done using analog circuits, so large analog circuits that would have voltage comparators in there, and if the voltage crossed over a certain threshold, that LED would switch on and so on. But that didn't really give you very much of a flexible solution where you could change what those levels were and so on. So with that in mind, the overview for this really is that if you look at the board, we have an input buffer and some kind of precision rectifier. And what follows that is that takes a precision rectifier takes your bipolar signal, which means it goes positive and negative. It makes it all positive, so it basically flips the negative part so that they're all positive. Because we're not listening to this circuit, we're viewing it. We want to know what those peaks in the audio are. So that all goes into a microcontroller. The signal is flipped and scaled so that it fits into the maximum voltage that the ADC here can handle. And then inside the part, then it's run through a low-pass filter, and that controls how quickly the jumps happen. And then it also runs into a software comparator, which compares the data value of the voltage at that point, along with the threshold. And then that drives an LED array. Now what we have at the bottom here, we have a couple of switches on the board so that you'll be able to, on your final product, switch between switching peak hold on or off. And we'll also have a serial port so that when you get this home, when you get one of these boards home and you want to set up your custom LED threshold, so if you want 3 dB steps, or if you want 1 dB steps where it's almost clipping, and then larger steps as you go down the range, you can actually program them in yourself using a very low cost serial USB to serial port adapter, which we'll also have in the XCloud Audio store. Anyway, that hopefully brings you guys up to date. Let's talk a little bit about what and how to test these boards. All right, so the purpose of a debugger and test board is we want to program the microcontroller that's on there. So with our firmware is software that actually runs on the microcontroller itself. We want to debug, so if we have any reoccurring problems with early batches and so on, I want to be able to understand where the problem is without having to break out all the tools and everything. So I want to quickly be able to say, oh my goodness, there's a problem with my front-end buffer, for instance, and be able to test those very, very quickly. I also want to do a functional test of the board. And so what that means is testing that all the functions are working, and not only that, but making sure that everything that you guys see as users is open and available to you. And then burning in as well. That's something I'll be doing on the first batch of boards that I do, is plugging a board into it, for an hour or so or overnight, and just seeing if there's any behavior changes over time and temperature. All right, so programming the board typically comes from using a serial port, like a USB serial adapter, or what could be called a JTAG programmer. JTAG is an industry term that's typically used for debugging and programming, large DSPs and so on. But it's also a search term that you can use. And so, for instance, what you see here, this is a JTAG programmer for Atmel devices. This is the one that's used these days for like MSP430s. Arduinos are quite special in that Arduinos are actually programmed with a bootloader integrated into them. And what that means is that someone's already connected an Arduino to a programmer, downloaded a special code that lets you write more code into the system using a serial port. But otherwise, most bare microcontrollers really come with nothing running on them. You have to program them with a programmer. Now, what we're going to do with these boards is actually use, this is an MSP430 Launchpad, and it's actually used to develop code on itself. It's got a section of the board that's actually a programmer. So this section here that you can see me highlighting with a mouse here is actually does the same as this board here. And so what you do is you plug your board, you can basically remove this chip, and what I'm going to do is bring signals up from here from the programmer. I'll bring power, I'll bring the programming signals, and I'll bring the USB serial port data up to the board. And the reason I'm using that instead of integrating this onto my own circuit board, because I could, TI actually makes this pretty open. I could copy and paste this into my own board. The reason I don't want to do that is because these are low cost enough. These boards are about $10 these days, and they're already guaranteed to work. So it's one less thing that I have to test. So, and I only need to build one or test one. So it's just easy for me to just buy this, know that it works, and program the board from there. All right, so let's, now when it comes to debugging, ideally what I want to be able to do is separate the circuit into segments and test individual points. I should say points, not tests, my bad, if needed. And so, and then I can bring those signals from different test points out to automated or manual test points on the board. And the automated ones will be signals such as the serial port that can come back through USB to the computer. It could also be something that connects to an oscilloscope, a digital oscilloscope that's running a test program on there with pass-fail parameters and so on. And then my configuration switches, for instance, down here, I could bring these to an external switch or an automated switch, just a transistor that would clamp both ground and that signal point together to be able to, on the fly from an automated test program, to switch them. And then the serial port, I just mentioned that will be running back and forth to the PC. Having this data also allows me to very quickly, if I get a board and it fails test, I know exactly where in the test it's failed, which in my mind is actually a very powerful tool. It's something that I can very quickly spot where there's a problem and take it from there. So following that, can move on another slide. So the features I want to test here, of course, I need to test that the LED array is working. And with 10 LEDs in very close proximity, there is a chance that one of them may be placed incorrectly by the pick and place machine that I have, or not enough solder paste, or some other manufacturing defect. So by being able to for instance switch on all the LEDs under my control, I'll be able to very quickly see, okay, you know what, I've switched on 10 LEDs, I have this much, I can see 10 LEDs, that's a pass. I also need to test the input buffer and precision rectifier. So if I know what signal's going in and I know what signal's coming back out, then I should be able to compare both and say, okay, this signal is working just fine. Configuration switches, again, this can be, I can test this by connecting those two pins together and seeing if the LED sequence that comes out of it works fine. The serial port, I'll need the serial port to program the thresholds, the default thresholds in the device. So they'll be tested in real time on the board. And then input calibration is probably one of the first ones I should be doing, is making sure that my trim resistor that I have on the front end can be turned appropriately so that enough signal is getting into the device. So let me just, there we go. Sorry about that, folks. Okay, let's move on a little bit. So the tools I have at my disposal here, I have an audio signal generator that can generate up to 22 dBu signal. So that's really my overload point for most equipment I'll be plugging into. I'll be setting the maximum signal into the tinyVU as 22 dBu. And then it's up to you then as the user to, you can either keep it like that or you can trim it down to whatever you think the maximum signal will be out of your product. I have an oscilloscope. a trusty Rigol DS1052, which actually has a pass-fail mode, which I haven't researched too much. I've watched a couple of YouTube videos myself, but essentially you feed into it what your perfect signal is, as in what you really want it to be, and it creates a window around that signal. So basically it says, you know, if I get a 1 kilohertz sine wave of 1 volt peak to peak, if I get exactly that, then it passes. But if I get something that's 2 volts peak to peak, or if I get something that's 10 kilohertz instead, that'll be seen as a fail. And I can read that back either visually, you know, looking at the oscilloscope and it'll flash red, or there's a potential I could create a software tool that would read that from the oscilloscope. Now, the PC with the basic serial port software, I think I've shown that in last week's show and the week before. That's mainly about driving, you know, the serial port so that I can, you know, type in commands into the board without needing that special programmer. All I need is a $5 or $6 USB to serial TTL converter. Very, very easy to use, and nearer the time we'll actually talk through some of those. And then finally, the microcontroller programming tools on the MSP430 Launchpad. We already spoke about those, but basically I'll be using the development tools that they provide to download the firmware every time. And then bonus points beyond this truly is automating that test flow. So I spoke a lot earlier about measuring everything visually. Oh, are all the LEDs on? Did things happen when I expected them to? The real winner here is how can I automate this so that I can guarantee quality every time? You know, it's really nice to be able to do things quickly. An automated test would mean I could fly through this test and it would take, you know, seconds to test each board. But really, it's more about quality and making sure that when I test the next batch of these boards, which could be a month or 2 months between each build, I'm doing exactly the same tests and delivering exactly the same quality of product. And so, you know, in the pros league, in semiconductors, in some semiconductors and in some real end equipment manufacturing, they use a tool called LabVIEW. And LabVIEW is a tool by a company called National Instruments. Let me see if I can find a window here to show you. This is part of NI's website. And essentially, there's a whole video for it, but essentially you can develop test systems with it. And so what that means is that it can actually talk to various pieces of equipment, such as a signal generator, a signal measurement tool, you know, any custom hardware. For instance, if I wanted to use a light-dependent resistor to measure if the LED was on or off, I could do that and talk to it with LabVIEW. And it would, you know, store the results per board as well. So it's really quite a powerful tool. Now, if I'm going ultra cheap, but with lots of spare time, then I can use a programming such as Python, a programming language such as Python to do a lot of this. So providing all the tools I have speak serial, meaning RS-232 or TTL serial port languages, then I can very easily just serial port in and out of the device, and, you know, send a command such as, you know, switch on 1 kilohertz, 1 volt peak to peak, for instance, and then, you know, the same with talking to the oscilloscope and saying, is this a pass or a fail? Now, if I do that, it opens up the capability to read the serial number from each IC or each board that I test, track the results, track calibration. You know, if a board failed, I could track what I do to fix it and so on. And it's very pro. I mean, that's the best term I could think of right now. Is that it's really a professional way of guaranteeing that the test is the same every time without doubt. So very, very cool. So that's the end of like the PowerPoint brainwashing, if you will. Now let's talk about how we actually develop that board. So we're now going to step into, you know, drawing and so on with Eagle. So let's dive in. I think that was the last slide I had. Okay. So firstly, let's start off with an example of one I already started with, and I actually decided at the end, recently, because I designed it a long time ago. I thought I've learned a lot since then. Let's start again a little bit. So let's do projects, level meter. Where's the level meter? Level meter, and then we'll do test hardware. And sort of here's one we invented earlier. And this was done in the old version of Eagle as well. All right, so what I did, okay, hopefully you guys are seeing this. This board pairs on top of that MSP430 launchpad that we had. And so these two long headers down the side here, this one and this one, are actually mirrored or paired to what's on that launchpad. And essentially I have an array here of the footprint, sort of the screw holes and so on, and the pins. So for instance, these are your dedicated programmer pins. This is your analog input pin, and here we have the serial port connection and so on. And what we do basically is tie all this together and then plug this board on top. So this board truly is designed to just mate on top of the board, and off we go from there. And so let me rephrase this. This board will plug into the MSP430 launchpad, and there'll be a stable, steady board screwed down and so on. And then I can, with my individual VU meter boards, and I can either hold down with my finger or use like a toggle lever that'll just apply enough pressure onto a bunch of pogo pins. I just realized that some of you that may have dialed in last week may have seen what I was talking about, but if not, let's see if this works. Okay, pardon the whole screen for the other camera. But for instance, these are pogo pins. So what you're looking at here is an early version of the Eden test board that we have. And it's actually an Eden board. The Eden is a microphone preamplifier that we sell at Expat Audio. But what it has on here are springy pins. And these pins are actually brought out to a power supply, an input signal and an output signal, and then a pot to control the gain. And so all that goes in and out of the audio tester that I have, and I can set up gains and so on. So that was 2, maybe 3 years ago when I developed that. I've learned a lot of other tricks since, and I'm hoping to really integrate those into this board. And so there's a couple of things in this board I really like. There's a couple of things which really annoy me. And so what I thought I would do is remove a bunch of things from the schematic, keep it fairly simple, or we could actually go back and start a new one. So let's go to the schematic, and then we'll walk through the schematic, I think. Okay. Okay, so here is the pin out and the pin names for all the pins on the VU meter board. Okay, so I have power, I have a ground signal, I have a signal called rect audio, which is the rectified audio, and then TXD, RXD. These signals are used for the serial port to communicate with the device. And then I have all the GPIO, the general purpose IO pins, which are used to drive the LEDs. Okay. And then on the other side, same thing here. And then SBWTCK and SBWTDIO, these are the programming pins that are used to program the device. Alrighty. So down here we have these two pin headers actually represent the LED array and the pins between them. So if I jump here, we show you guys in real time. Here we go. So on this board, you have 2 arrays of pin connectors, one there and one there. And the idea is if you only want this little board on your front panel, then it's very, very, very easy to transfer the signal over. So I'm sorry, let me say it the other way. If you're willing to put this whole board on your front panel, then it's very easy, just put some wire bonds between them. But if you only want this board on your front panel and this deeper in your case, which in my case, I want the VU meter to take as little front panel space as possible, then I will cut this out along this V groove and use a ribbon cable between one and the other. Now to emulate that ribbon cable, I use you can see it here. Here's one pin array and here's the other. And so I tie the signals across. And this is my virtual ribbon cable, if you will. It also means I can test the board and not modify the board while I'm testing it. And then these two pins here are actually ground, because in Eagle I can flow all the ground with one button. All right, so let's, this is the new Eagle, so I'm still learning. Okay, so that's that part there. You can see here these headers are already in place. Now what I actually did for this was I copy and pasted the entire design, or actually started the design from the VU meter board, and then I just deleted all the other components that were in the middle because they are under test right now. And they're not needed on this particular board. All right, so let's go back to the schematic. All right, so we've actually talked about these connectors, this connector, and this connector. Now, I put a bunch of these headers on here just so that I could have a prototyping area up here. So if I need to add any extra circuits or anything, I've got a bunch of holes that I can just solder into and so on. So it's a very easy, very quick way of just adding a debugging area in the corner. Pardon me, talking this loudly for this long requires a nice cup of tea once in a while. Okay, so my audio input signal is at this JP3, and one signal is ground, one signal is VCC. By the way, I just wanted to mention, you may notice that these straight pin headers are actually slightly off-center. You can see here, even though the pin itself is designed down here, these holes are slightly off-center. This is actually done deliberately. It's a library by the guys at SparkFun. And what it's used for, because if the pins are vertical and they're slightly offset like this, it actually holds the pins in place while you're soldering. So normally, you can see here the pin shown in white here is slightly smaller than the actual pinhole. And so what I found was early in my days of doing this stuff was that I'd put the pin array in, and then I'd flip the board over to solder it, and the pin array would fall out. Or if I put my finger on to hold it in place, I'd either burn my fingers, or it would be off center and so on. So what this great little library does is it just keeps the pins in place beautifully. It's really worth trying out. And I'll post a link to it on the YouTube and in Facebook if there's any interest. So this analog input signal here, it's probably easy to show it on this board. I actually run it into one of two places. I can either run it into a test point. I can run it into a switch, and that switch is actually going off to this potentiometer, or to this input connector by here. Now this potentiometer is connected to 3.3 as its maximum value. So with this, essentially, I can either send a real audio signal in, or I can trim from 0 volts all the way up to VCC, and so 3.3 volts. And so it's a nice way of sending a DC signal into the board and just testing manually that I can switch on all the LEDs and so on. Pretty useful. However, it's annoying me a little. And the other thing I didn't do a good job of on this board, and I'm kicking myself for it now, is ideally I should have put something like a 3.5mm connector on this board, a headphone jack, so I can bring the audio signal in. I'm really starting to get annoyed with having fly wires for everything, especially on something that's kind of a finished product style of finished board. In a perfect world, I would bring a USB connector and a USB DAC and everything would be hooked into a hub, and then, it'd be really, really cool. But again, I'm building one off of this. What I just truly want is something that's reliable and, just freaking works. So one of the things I'm considering doing is chopping down this area here, this prototyping area, and simply putting in a 3.5mm jack here. And okay, if I can stop clicking as well, sorry about that, folks. The area you see here, these are pinholes for the actual for the board itself. These are used to align the board with these pogo pins. So these pogo pins ideally, go into a hole on the board, and so you have to pre-align the board before you start pushing down. Otherwise, your test pin will be off from where you're testing on the board, and so on. All right, so let's jump back for a short moment to the actual board itself. Where's that project? Level meter and the board one. Yes, I want to load. Okay. So here's the, let's go to nice view. Oh, I hate this view. Nice layout view. Okay. So on this board, this area here is that front end we spoke about. It does the buffering, and it does the precision rectifier. Sorry, I was having a bit of a moment there. Now, the only place I actually bring out that precision rectifier point, and I'm kicking myself right now, is at this point right here. And this looks like a test point that is only on one side of the board, so that's really annoying. Looking back, I really should have created like a through-hole point that I can test with. So the challenge is now, can I see what my test signal is in my from underneath the board? Because ideally, what I want to be able to do is plug this board on top and test that point. And so there is this point here that is $N$14. That's the node of the circuit at $N$14, and it's between this 100K and this 800. Well, these actually became, I think I was 12 ohm in the end, because I didn't need this low pass filter. So ideally at $N$14. So I'm going to go back into Eagle, and I'm going to do show $N$14. That's that node. Pain. That's a real pain. Okay, so to test, what you see in red here is the top side of the board, not the bottom. So there's a lesson here for you folks. Think about what you're going to test before you start the board, the actual board, the product itself, rather than at the end of it. So again, this board was designed 2 years ago. There's a lot you can learn in 2 years. Darn. Wow, that's annoying. Okay, so one of the things I can do at this point then is add a test point, an oscilloscope test point here, or put it into my test program where I tell the operator, hey, take this signal from, manually take the probe and put it down at this point. It's not ideal, and should I want to do a board in the future, one of the things I'll actually do here is put a real hole in the board here, as in just like these vias. Add a via here so I can come underneath with a pogo pin. And one of the things I may want to do at this point when I'm making this test board is put that pogo pin there and not populate it at this time, but say, okay, when I do get around to making version 3.1, adding that pogo pin, adding that via so a pogo pin can measure that voltage at that time. Okay, so I'm so frustrated with that now. Okay. So you can see the signal here. This N14 is there, and then after that it comes across here and directly into the pin on the MSP430. So I have no access to that signal from underneath. Okay. So let's skip back to the schematic for the test hardware. Okay, so here are my pins over here as well for these are the actual connectors I have for the MSP430 launchpad. Always have a little bit of decoupling. I've found actually, you know, I was raised on having, you know, a big 10 microfarad electrolytic cap and a 0.1 microfarad ceramic cap whenever I do decoupling, and it was, you know, kind of, oh, you have an analog circuit or a digital circuit, you have to put these two capacitors in. What I've discovered over the years is that you can get ceramics now which support, you know, up to 16 volts or even higher at that 2.2 microfarad value, so fairly cheaply. In fact, I buy a reel of them for about $20 or $30 and I'm just done for the next decade, I think. So yeah, yay for higher value ceramics. And then I have a UART connector here. This actually came from the original board, and this SPY-BY wire, which is the TI's JTAG term. Again, that's on the actual board itself. And then what you see here then is the signals that I'm using for this test board. So I have either the DC input that I can switch in, or the analog board. Or something that can I can select. I can test what's coming in as well, and, you know, send it off to the analog board. Now, what I'd like to do here is add a different 3.5mm jack. That's something I believe I have, and so there we go. So let's open up the latest version I have of this board. So I did start working on one. There we go. Okay, so I think I've removed that testing area. And if we look at the board, it looks like it's much smaller for starters, because I was able to trim that out. And I actually moved everything to underneath the board. And the reason I moved everything to underneath the board is, I think on next week's show, we're actually going to create this PCB using my laser engraver. So if I can make everything single layer, or, you know, near to single layer, then we'll you know, maybe a couple of bond wires over, we'll make it in-house, because, you know, I could send this off to be manufactured elsewhere, but truly, I'm not certain it's really worth it for a one-off board if I can simply manufacture it at home. The other thing is that a lot of these trace lengths, trace widths are wide enough that I could self-etch this at home. So stay tuned for that. So let's look at the schematic. Now, we talked about adding a headphone connector, and so this is the truly boring bit if you're not into CAD or anything like that. Come on, chop chop tabletop. All right, let's bring this in. One of the things I do with all my libraries in Eagle, and the ones I have made for me, I get them made for me now as well, is I tag them EA something. That's expat audio something something. It helps me to find all the ones I've worked on. And you can see there's a bunch of TI devices here as well. I kind of got a lot of them made. And I have a headphone connector here somewhere. There we go. So here's the factory. I'll share with you a couple of things here. Let me just place it first. Here we go. All right, so let me place it, and we'll talk about how I get my libraries made and so on. Okay, so typically with a headphone jack, you'll have some kind of on the modern ones, you actually have a sensor that tells you if anything's been inserted. So that's how your cell phone knows, for instance. One of the ways your cell phone knows if you put it in your headphones. And then you'll have signals left, right, ground. Or if you have more than that, then you'll get left, right, ground, microphone, or left, right, microphone, ground, and so on. So if I look up this connector, and one of the things I can do here, let's talk about how I get the library made. I used to make all my own libraries for Eagle, and in fact, I even used to outsource that service as well when I had more time, before getting married, before having kids. Now I go to Fiverr.com, Fiverr.com, and there's a guy on there called his username on there is Mochini, Mochini, and for $5 he makes you a library. And in the end, I actually went back to him with a specification of how I want him to make the library, and so he does everything for me now. It takes a little longer, I can't get it in the next 10 minutes or next hour like I used to, but the libraries are made to a consistent quality. They're made for me so I can focus on other parts of the project. So yay for outsourcing. So if you look at this connector, bear with me. And these connectors actually found on eBay and bought 100 of them or something for like $10 or something. They're ridiculously cheap. Unless you need them really, really quickly, or you're making a product that has to be sold into the military or something, don't buy connectors from DigiKey. Honestly, it's daylight robbery. So I'm just waiting for this data sheet to load. Oh yes. All right. Let's rotate counterclockwise. There we go. All right, so you can see this is a single connector. It's actually got a couple of little dimples in the bottom of it to stay fixed to the PCB. We have a copper side view here of the board. So the pin numbers, and then we actually have the pin out as well. So this is typically shield. This will be a ground or shield, and then you've got the 4 pins coming after it. So what I'm going to do is I'm actually going to connect. I'm going to connect these two. So these are the frontmost pins. I'm actually going to connect those through a summing resistor. So it acts like a bit like a mixer. Very, very small value, maybe like 100 ohms or something. So that regardless of whether I get a test signal on left or right, it'll work. Pin 4, I'll probably connect to ground. And pin 5, I'll also connect to ground as well. And so when I plug it into, if I wanted to use my iPhone, for instance, as a test signal, the iPhone will detect this as a stereo output or a mono output headphone level. And then this is just as headphones, no microphone involved. Sorry, I did a really bad job of describing that, but bear with me. So let's grab ground. And one of the other things I like to do is I like to treat, every time I start another page in a schematic, the first thing I do is I copy over the power supply nets. That's what I want, isn't it? Oh, that's naming them. Hold on. Control lines. There we go. Sorry, I'm used to the old Eagle icons. Okay, so that's connected. That's connected the shield pretty well. I'm also going to connect the microphone or the second ring. So typically you get tip, ring, shield. So I've just connected the second ring to ground, and then these two need to connect through some summing resistors. So let's grab those. Do I have any other resistors on this board? No, I've been terribly efficient. Okay, so let's add a resistor. Now in Eagle, most people simply use the RCL library. Where is that? where are you? RCL library. This is resistors, caps, and inductors. And they'll use, for instance, and they'll pick the package they want from here. So whether they want, through hole or surface mount or whatever they want to do, MELF resistors. I've used these as well, but I actually created my own passives. This is what I want. Resistor. Now I use 0603s for almost everything. So this is a the only thing I added with this is that there's a small white silk screen that goes around the resistor to help me understand which way the resistor should go. Because typically what will happen, let's say I have an array of resistors, like one next to the other. When I'm doing the pick and place, if I have two resistors next to each other, it looks like 4 boxes, and I may not know which orientation they go. So having that little white silk screen that basically says this is one resistor, this is the next one, really helps. The other thing I can use here is a little one that I made called a combo resistor, and I'll show it. Let me just add it here, and I'll show you what it looks like in the schematic, in the layout. Okay. So my combo resistor is actually 2 packages in one. I have a surface mount one, and then I have the 2 main connectors here and here. Well, I found that actually helps with, if I'm doing quick prototyping, I need to change the value, I use the through hole, and when I'm in production volume, then I would use the surface mount. All right, so look. All right, so I've seen some feedback as well. I just had a quick look to see, if there's any feedback or anything. 2 folks have commented so far. Andy, please watch the replay. I'll put it onto YouTube. And Joseph, I'm real sorry, man. I think my internet is playing up here. We're doing the best I can, but this will be available on YouTube later as well. Please go ahead and ask your questions there, or come onto the Facebook group as well. Sorry, I can't do much more than that right now. Unless you want to call AT&T for me and yell at them. That would be really nice too. All right, so I've got these 2 summing resistors now. I can make these any value I want, really. But ideally, I want them to be low enough so that they don't actually impact the input circuitry on the board. So what I was thinking, if I keep these down at sort of 16 or 32 ohms, then as far as any audio source I have is concerned, it just looks like a headphone. But also, my buffer is actually using very, very high resistors because I didn't want to draw any current and so on. So adding 16 or 32 ohms to something that's already 10k ohms is noise. So I'm not going to worry too much about that. So I'm actually going to sum these together at this point here. And I'm going to bring this signal. Where do I want to bring it to? I actually want to bring it to analog in. So I'm going to bring this down here, cross and up, and put that there. Yes. Okay. So at this point, what's going to happen is, yeah, that should be okay. So if I have this switch in position 2 and 3, then this signal is going to come in here and drive the analog input to the board, and I should also be able to sense those at JP4, JP3. In fact, I don't need JP3 at this point, so let's remove. Will we remove that? Yes. Let's remove that. I remove here. Oh, I hate these new icons. Delete. I don't know why they added them. Okay, so I can now bring my DC control signal through here or up along here. Now, one of the other things that I picked up on as well, and some people may be like, why on earth are you using these old, huge potentiometers? One of the things I did learn about those small little trim pots is that they're not actually designed to be turned a lot. They're only designed to be turned, sort of 100 or so times. And I'm going to be building more than 100 of these boards. So I wanted something that could last I don't know 10,000 turns or more, and so that's where these old big old 16mm values come from. All right, so And once I'm in this other mode, once the switch is between 2 and 3, then I can actually go from either from JP4 and through, or if I don't connect anything to JP4, I can come in through this headphone connector, and it doesn't matter if I bring the signal on the left side or the right side or both. It should work just fine. Okay, so let's move along a little more here. Okay. So let's work on the layout for this. I've added these extra components. Let's move these generally up into this space before I zoom in again. By the way, folks, if this side of the design process interests you, I can do more videos like this. I enjoy working in Eagle. I find it quite relaxing. But yeah, please do let me know. I'm going to flip this board. Okay. Now, one of the challenges I have here, I'm just scratching my head a little bit more. I want this board to be a single layer, so there's only copper on one side. And so, if I do this, then I actually have these pads for this surface mount connector on the wrong side. So one of the things I can do here is if I mirror, everything gets pushed to the underside. And so I can now place this near the edge of my board. And probably push it down a little. Here are my summing resistors. So if I zoom in a little more, you can see I can bring my nice and thick. You may be wondering to yourself, why on earth why am I making these traces so thick? Because when you're hand etching stuff, the standard thicknesses you get are ridiculously stupid and dumb. There we go. Add these two together, and I'm going to bring them together. Oh, there we go. I already knew. Huh. It's not what I want. Okay, my schematic didn't work there. I actually want to be able to connect this point to JP4 and have it go to number 2, not over here. So I think, let me go back to my schematic. Oh, look at that, you little beggar. All right, so you can see what I did wrong here. Let's delete that link there and actually bring it over here instead. And let's just check what the name of this is. Yes, okay, so now if I switch this to DC, it's still DC, and if I switch it the other way, I'll get the values from here. And while I'm doing my excellent work, let's make sure this is like 32 ohm and another 32. We'll see what's on the other thing is I have to see what's on the pick and place machine as well, or maybe not so much because I'm already running with, I'll be hand assembling this board. Okay, yeah, and so now I can see that my board is behaving a little better now. So you can see that this signal here comes cleanly down, and I'm going to do a rat's nest. And what my rat's nest does is make sure that everything is pretty good. In terms, so a rat's nest will float ground everywhere as well, so that helps a lot. Okay, and it looks like I only have one problem area here. So this is one of the advantages of using the rat's nest command. The rat's nest command actually tries to connect everything together. So what I've created here, what you see in all this blue is a polygon. A polygon is an area that you define and you tell it what signal you want to go inside. So for instance, if I create a polygon, and I'm going to put it on the top layer, and I'm going to call it ground as well. I can actually draw a square by here, and I'll delete it in a moment, but just to show you guys. And then when I rat's nest, when I call the rat's nest command, it'll fill it for me, or it should do at least. Why didn't that fill for me? Let's remove it. Draw, view, redraw. All right, so let's do this one more time. Let's find out what this is. Yeah, I think this is ground as well. Okay, let's remove this and I'll show you guys one more time. Okay, so right now I have the main signals which are not connected are ground, and I can show that by doing a show GND. And you can see here that through some miracle I need to connect this point, this point, this point, this point, these two, this, and these up here. And so what I'm actually going to call here is a polygon. I'm going to put it on the bottom of the board. I'm going to say I don't need it to be a width of 50. I can have a width of 0. I'll call it ground. I'm going to start here. I'm going to draw a square around my circuit board. All right, now if I hit rat's nest, it should at least equal 5 did this. We'll soon find out if equals 7.5 does it. There we go, it's filled in all the gaps. Now, in the surface mount world, this is awesome. I'm very happy. However, one of the things that's critical is my isolation. I need to be able to isolate my traces much more. So let's say I add, let's go extreme here, 50, isolate. This is going to be 50 mils. You can see immediately what happened. It actually separated the ground area from the trace itself by 50 mils. Now if I go back to the world of millimeters, which is where I'm much more comfortable, I've added, should give me an isolation of 1.27 millimeters. So I have 1.27 millimeters between every trace and everything else. And so if I pull a rat's nest now, you can see, because I've got so much distance between the ground fill and the trace, ground hasn't actually been able to fit between spaces and so on. So one of the challenges here is this one. Let's shrink this down a little. This is just a little bit less than, just a little over 0.5 millimeter. And rat's nest once again, and you can see, for instance, the rat's nest here. I'm going to get rid of you. Oh, why? Yeah. Okay, smash. So it's actually filled in a lot of these gaps. Now, one of the things that's suddenly terribly annoying to me is top docky. Is actually a lot of the names, like the silk screen and so on that I had on here, has actually taken up copper, and that could cause problems as well. So for instance, you can see this tiny sliver of copper here and this. So we're going to go through and fix that in just a moment. I don't know why it's done that. I need to look into that why. But everything else here, it's flowed. Almost everything else is flowed except for this little guy here. So this ground pin is the main ground that comes up to everything else. So I need to work out some method of getting ground out of the board. And so, one of the ways I can see this little gap by here, I could manually route that. So let's see what it takes. Okay, the line I drew there, so let's thicken that up a little bit. Width 6. So you can see that 0.6 is not enough. Yeah, I'll probably have problems with that. 4. And that looks kind of a bit more realistic. So if I've got a couple of options here. Here's 0.4, and we will call this. We'll rename this ground and thicken this line up a little bit. So I'd thicken this to 0.4. And I could bring this all the way up here. Oh, I don't know why my width is down to 0. There we go. All the way up. And in. Now if I rat's nest, it should be as happy as a clam. You see here it says rat's nest, nothing to do. Woohoo! Okay, so my only challenge now is that these two traces are incredibly close together. So I'm going to bring this in a little. Now a little here means I have to press the Alt button, I believe. There we go. And the Alt button just allows me to go, rather than big steps, it allows me to go in little steps. Okay, so that's one way I can do this. Now if I have any problems with that pin, I'm actually also going to add 2 veers or holes into the board. Yeah. I'm going to make sure that that veer is big enough for any wire that I have. I'm going to add one there, and I'm going to add one over here as well. And the logic in my madness here is that this becomes ground, and also this becomes ground, so that if I have to, I can stitch it over. And let's bring this down, round, in. And again, rat's nest, nothing to do. So, okay, so now let's go in real quick and fix some of these issues, like this JP9 here. What I'm going to do is I'm going to grab this spanner. I'm going to use it to change the layer. And I'm going to tell it, hey, just tell it to use top document tdocu. Here we go. All right, so let's try this one. And let's try rat's nest. There we go, look at that. So now I can come in here and go 1, 2, 3, 4. There. Now I'm sure there are far faster ways of doing it than this. I am, quite frankly, too lazy. No. Oh, that's interesting. Where is the... Oh, that's interesting. I don't know where the how to select that view meter. I'll come back to that in a moment. Let's fly through the rest of this quickly. Layer, tdocu, 1, 2, 1, 2, 3. Also, what the heck is this doing over here? Oh, crud. Huh. Okay. Come back to that in a moment. It appears I've lost my input connected to, my actual input connected to the board. That's going to be a problem. Shoot. That was perfectly placed as well. Okay. Let's go back here. There's a lovely lesson for myself here, which is don't do development like this in front of everyone. Don't make mistakes in front of everyone. Add this. Okay. Well, now I'll need to double check when we So I'll have to double check the spacing for this versus this, and I need to make sure that the ground is right around and so on. That's to do, and I'll have to remember to do that. Let's carry on changing names and so on around here. There, 1, 2, 3 more. View all, show all. Well, I can't for the life of me work out how I'm supposed to change the text there. Where did that go? Answers on a postcard. Let's sort out what layers we want to look at. None. Look at the bottom, and I want to look at bottom origins. Okay, and top origins as well. Okay, so this actually gives me the origins for each of these pins and devices and so on. But one of these should highlight the text. What? The PCP logo. Try. Aha, there you are, look at that. So let's add those to top D doc. Top docking. They'll disappear because they're not in the nice view. There we go. Ooh. I'm getting nervous for a while there. Okay. It looks like I need to connect this. Oh. There we go. All right. So I'm quite happy with that. There's a couple of things I'd like to check. So let's save this as it is and go back to a previous design that we have. And let's have a look at the board. So here's one we cooked up earlier that we've modified since and actually brought into the new tools. And you can see here actually that this pin here is actually a little sort of further south than the origin here, and a few more pins over. So I'm going to count in boxes here. They're 25 mil each. 1, 2, 3, 4, 5, 6, 7 to the center. Okay, so 7 from the center of this connector to there and 1 down. So I can take care of that, and analog in is actually the closest signal as well. So that's 7 and 1, 7 and 1, 7 and 1. 7 and 1, 7 and 1, 7 and 1. By the way, I am aware that I click my teeth way too often. Sorry guys. When I do remember, I stop doing it. Okay, so let's go back to mils for this one as well. These are 25 mil steps, and so this is the middle, so it goes 1, 2, 3, 4, 5, 6, 7, and down 1. Voila. Now, one of the things I'll do before actually manufacturing this board as well, I'm actually going to have to print it out and then measure it again. So that's not lost on me. That's not forgotten. Let's have a look here. And of course, because I moved things, now all my traces have moved around as well. Okay. And let's add up the width on this again. Remember, the wider the traces are, the easier they are to etch and so on. So it's definitely in my interest to where possible, make the traces as thick as I can. And so that was 32 mil or in regular speak for the rest of the world outside of the USA and Lebanon, that is 0.6 millimeters. Now, realistically, that's actually pretty thin, but truly it's the isolation that truly counts on this. But I'll show you guys how I can try and make this board on the laser engraver, and if it doesn't work, we'll do it the old way. Width, there we go. Oh, that's not what I wanted. Width. There we go. Yeah, I could probably go even thicker than that. The challenge truly is, let's nest this. Okay, the challenge truly is not to make it so wide that the trace plus the isolation block ground from flowing. And so let's width. I mean, I could make, for instance, from here to here, I could easily make this a 1 millimeter trace. In fact, I had more than 1 millimeter, which is wonderful. Of course, when you're etching, the wider the traces are, the more error you can have in the amount that you're tracing. So you can leave it in that tracing bath for a little longer. It doesn't matter too much. Let's see. Yeah, you may want to turn down your speakers for just a minute if you don't want to hear click, click, click. Any suggestions for a quiet mouse are always appreciated as well. All right. Now, yeah, we know this little trace here is a little bit too sensitive or narrow, even though it's round, pardon me. Ooh, that was a bad move. Let's undo that one. Okay, so now let's do another one. And the way I know everything's connected is I check the rat's nest. So it tells me there's nothing to do. Okay, so I think that's about it. Let's have a... I think I've gone and done it again, haven't I? Let's check the schematic here for just a moment. It's good. Fine. Well, that's weird. So if I look at my schematic here, I want pin 2 to actually go to analog in, but analog in isn't actually going to the board. Oh, that's a good catch. All right, so sorry guys, I thought I'd share this with you. So I'm looking at my switch here. My switch was designed to select between this DC controlled value and this music or whatever coming in, or test tones coming in through the headphone jack. And so this test point 1 should show me what exactly is going to my device under test. However, right now it's running from this headphone jack, which assumes that only the headphone jack will work, because this signal, even if it goes to the middle here, never gets routed, which is not what I want. So a quick look at the schematic here, and I had my aha moment where I feel really very, very stupid, is that analog in right now isn't going anywhere. It goes to this test point and that's it. This here is my connector, my board, and I'm going to show you what I do here. Make it a little smaller. There we go. And we're going to rename this. How do I rename this tool? It's a long time. Name. And I'll log in. And Eagle's going to ask me, do I want to connect them? I'm going to say, yes, sir. Yes, please. Boom. All right, let's go back to my layout. Look at that. Look at that. Look at that. Oh, dang. No, that's the wrong one. Shoot. Sugar even. Oh, I was so confident. That'll teach me. JP3 needs to connect to survey says. Yes, okay, so let's rename some of these now because it a-in spare in. It's a spare input. JP4 is like a analog, and then we'll call the this is the switch. So source switch. Back to my tools. Okay, now we're living happily ever after. Now, one of the things I can do here, check this. If you guys don't know about this, I want to do an electrical rule test. Check. Here we go. Let's see what it's whining about. So I have 10 warnings. There's no. So I have a net here with nothing connected to it. Yes, you're welcome to complain. I was using those mainly for reference. Analog part, analog in has no value, so it has no part number right now. These are standard pin headers, so I'm not going to worry about those. But what it's not complaining about, and I was expecting it to, is that in my board layout, come on, tell me that. Okay, let's try the DRC then. Should tell me that this trace is now connected to the wrong thing. So if I do a design rule check, and let's just check it with default settings. Check. All right, here we go. So overlap. I have an overlap, 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 width, width. What's it complaining about for width? Probably complaining that the width of my polygon is too bad. So I'm not going to worry about that. And the actual overlap caused up here, I'm not going to worry about it. It's actually complaining that my trace is overlapping the pad itself. Again, that should still generate just fine. And then it's complaining about this one here because it's saying this shouldn't go onto this pin. So let's clean this up. Bye. Rat's nest, that's disappeared. Now I'm left redoing this one. So over, around, down, and beautiful rat's nest once again. There it is. And now if I run the DRC, the design rule check one more time, you'll see the only ones I have are the overlaps, which are connected with these components, and this this width one as well, which I'm not too worried about. All right, I should have. All right, so the next step in this process, which I'll do offline because this show's gone on long enough, over an hour, good grief, is I'm going to print this out on paper and then measure what the board looks like on top, and then we'll etch it and so on. We'll probably do that next week on Thursday, so tune in then. We'll have a bit of a shorter show, I hope, and yeah, we'll take it from there. My apologies this evening if the video's been low quality. I think I'm going to have to get a better internet connection, so Time Warner may be getting my business as well. Unless some of you